So now that we have all the data, the question I wanted to answer is the data accurate? Does it actually show an actual standard gait cycle? Gait cycle, which means a walking cycle of a normal human being. So this is the standard gait cycle right here. It starts at the heel strike when your heel first hits the floor, and it ends again with this next heel strike. And there are all these phases, and there are 2 phases and all these points. So in order to see if my data actually corresponds to a standard gait cycle, I took 3 milestones, which was the mid stance, the toe off, and the mid swing, and I noted where they come in the gait cycle, so at 22%, 60%, and 78%, and you can see those also in the figure. And I wanted to see if I take the mid stance, the toe off, and the mid swing of my data, would they actually come at 22, 60, and 78% of my cycle. So in order to do that, I implemented an animate function. So since I have all the data in an Excel file, I imported that data to MATLAB again and plotted all the points, and I can sort of animate the whole walking motion with a skeleton sort of plot. So I'll just showcase that. This is the animate function right here. Here we just read the Excel file again, and we, for every frame, we tabulate the X and Y values, and we basically just plot them, and some plot functions here that don't really matter. So I'm just gonna animate my Excel file, and this is the result. Here it shows the time, and here it shows which frame it is, and here is just my subject pretty much walking. This is pretty interesting. I enjoyed doing this part a lot. So this was a showcase. So I took that video and I found the first heel strike, the mid stance, the toe off, the mid swing, and the heel strike. And if you see, these stances are extremely similar to the actual stances in here, so I'm not cheating with the values. So I did tabulate them. The first heel strike is at 1.4 seconds and it ends at 2.7 seconds, which means the gait cycle is 1.3 seconds, and this was at 1.3 miles per hour. So this was our first trial. And here I note the values for the mid stance, toe off, and mid swing. And this is the percentage of the gait cycle that it should be at, and this is at where it's at. So for an example, 23% was 1.7 minus 1.4, which is 0.3, divided by the total, which is 1.3, and it gets 23. So it is actually very close to the actual values, 1% of error in each of them, which is, I guess, very acceptable. So the animate function is working, the data points are correct, and we're on the right track. So now I'm gonna do some analysis. What can we do with this data now that we animate it? We can maybe have some fun with it, animation, but for the purposes that we're talking about, more about the problems that we're trying to solve with walking and physical injury and all that, what is some of the analysis that we can do? Now there's a whole bunch of stuff that can be done, but this is something that I did, and I thought it would be like a simple, appropriate example to show. So I was measuring the joint angles. So I named them the hip angle, the knee angle, and the ankle angle, and they're identified here. And I wanted to see what the ranges were and how they varied throughout the gait cycle, in order to see for the 3 speeds, so in order to see the differences of what happens to the ranges of motion and what happens to our joints exactly when we up the speed or down the speed. Does it change at all? Is it just the same cycle but faster? Is the cycle a bit different? And that's what we were trying to see. So I called these vectors 1, 2, 2, 3, 3, 4, and 4, 6, and these are the angles that we're looking at. So before we look at this graph, I created the plot angles function, which basically also takes the Excel file that we have, which has all the data in it, and then these are also some initializations. Then for every frame in the data, we create all these vectors. The first, this is 1 to 2, 2 to 3, 3 to 4, and 4 to 6, the vectors that we wanted. It computes all the vectors, and then it computes the angle between. So I use the arctangent 2 function, which gives an angle between minus pi and pi, minus pi by 2 and pi by 2, which is the angle that we're interested in. And here is plotting the angles. So notice that the plot that I did is as a function of the gait cycle. So the x-axis of these graphs is going to be percentage of gait cycle. So this, at 1.3 it was 1.3 seconds, at 2 it was something else, but this allows us to analyze in the same way for the three speeds, because we can't just put a fixed time, because the speeds are different, it would change the analysis. So 0 to 100% of gait cycle. If we look at 1.3 miles per hour, we can see the hip angle. It starts at around 5 degrees, and then it change. I mean, if you kind of imagine this in your head, then the angles would make sense, but maybe it's kind of difficult to see from these graphs. But that's on it. Just take it at face value that these angles are correct, and these are the actual variations throughout the gait cycle, which is what we have. But I just wanted to show you the difference between 1.3, 2, and 3.5 miles per hour. So the question is, do the joint angles change as you speed up? Do the ranges change? Now when we look at 1.3 and 2, we can see that the knee angle is pretty much exactly the same. The hip angle ranges are also the same, and they're actually very close graphs. There is some small differences that may be due to some errors, but these are both considered walking, and the joint ranges are very similar. Now when we move to 3.5 miles per hour, which is actually in the running zone, so it's slow jogging, we can see that there is a change in these values. So for the ankle angle, which is the green one, we see that the variations are larger. So as we start running, the ankle angle gets more big and more small as we go through the gait cycle. So there is some change in the actual motion when we run. And the same goes for the knee angle and the hip angle. Well, I'd say the hip angle is kind of the same, but for the knee angle, which is the yellow one, there is a large difference in the range. So before we were starting at around minus 10 degrees, and then going down to minus around 55, and then going back up. But here we started at minus 35, and so it's the range of the joint angles are changing, and that means with faster speeds we're not just moving the same exact way but faster, but we're moving in a different way. Now I cannot make a conclusion now what is the impact of that, but further analyses can be made after this observation, and we could get some interesting insights into the way people walk. Now, what are the downsides of my 2D gait analysis? It was pretty cheap. It was not too complicated MATLAB code, although it did take me a long time to figure out the filtering. Number one, the camera maximum frames per second was 30. So as we increased our speed, the camera did not give as crisp images as it did for low speeds. There was some blurring, there was some stretching of the pixels, and this table just shows how many frames we could not get reliable information from. So how many frames we could not get the 6 markers that we wanted, and how many frames we got some very faulty data. And at 1.3 miles per hour we had 150 frames and we lost 0 frames for both. At 2 miles per hour we lost 1 or 2 frames for the video, but at 3.5 miles per hour there was some trouble with the camera, frames per second, and we lost around 8 or 9 frames from out of 150 frames, and that's could be an issue. The second issue is the placement of markers can be inaccurate. So the placement of the markers exactly has a lot of bearing on the angles and on the whole outcome. So right here, so I kind of placed them as best that I could, and there's the shoe and the clothes, so I just want the viewer to know that the data is extremely sensitive to exactly where you place the markers, and I did my best to place them in the exactly right locations, but who knows. This is a kind of cheap homemade experiment, so you just have to be aware that if you're using this method, that can affect your outcome. Another downside was that the hand was not considered, so no markers were put on the hand. It was because of the lack of time and some other issues. It took me a while to actually get this whole experiment working well, because the first 2-3 tries of taking videos and trying my my blob detection, they failed miserably, so it took me some time just to get things going right. And there is another downside, which the analysis is not 3D, it's only 2D, but I would say that's not very big of a deal, because if you have a frontal view of this image, while you're walking, there is not much motion of the joints in the direction of like your 2 ears in that plane. So in the frontal plane there is no much motion, so I would say that that's not extremely important. This is the most important plane that we're catching. And I just want to say thank you for allowing me to conduct this experiment. It was extremely fun, and I'll just play a video right now of me videoing my friend. It's just a MATLAB thing. Okay, play video on. This is just me taking a video of my subject walking with the markers on him. Alright, that was it. Thank you very much. Yeah, everything will be uploaded, and thank you.